In just the 2 lecture videos, we already finished the most part of chapter 3. Now we are at the final section, 3.4, coverage modification and stop loss reinsurance. Let me finish the typing here. Reinsurance. Okay. This is actually the most technical part of this chapter. There can be many challenging questions from this particular subsection. We have seen from chapter 2 that when we talk about coverage modification, we usually mean deductible D, policy limit U. Occasionally, we will talk about inflation and co-insurance, but the most important two are deductible and policy limit. Okay, so I think that's what the textbook focus on as well. So let's begin with the first one. Effect of deductible. So obviously here we have two models. We have individual and we have collective. Let's begin with individual. So let's call it A1, individual risk model. Okay, let's write down what we have from the previous results. Okay, let me get my usual color. Let's use black. Here we can easily calculate. So not calculate. Let's write it down. What collective model is. Okay. Effect of deductible. Let's of course we use D to denote deductible. So there are pretty much two things, right? One is N, one is X. So let's analyze the deductible. Obviously has no effect on the right. So deductible D, the deductible D has no effect on the number of policies or policyholders. N, right? So it doesn't matter what kind of deductible either you set or the customers choose. It has zero effect on the number of policies, right? Does not change anything, but it will change X. Previously, we use XI. Okay. Our textbook all of a sudden put subindex I. Of course, we usually assume the ID, right? So it really doesn't matter to remove the index I. I has 0 or 1. So probability is theta. Here, probability is 1 minus theta. And again, this means no claim. And Y obviously is the size of the claim if something happens. Once we introduce deductible, obviously that will change things. So let's put this notation. So after we introduce deductible, let's put tilde. Okay, because there's no effect, so n tilde equals n. That is the obvious result. Now let's study the new. So the new x tilde, the probability function PDF of xi is given by. Okay, let me first write down the result and then we will analyze why this is the case. let's put an index, although in pretty much all analysis, we have IID, so they are the same. The meaning of notation should be clear to you. For instance, this means, so here, this is obviously the PDF of Y, right? Okay, now let's take a look at this result. We are trying to understand why this is the case. So first, let's put analysis. So first we study the probability mass at 0. So X tilde is the loss after the introduction of deductible. So it may be the original size is 0. Then of course after the deductible it is still 0. That is because, right? I think we usually put plus sign as the subscript. So let's do that. Of course, it may be xi less than 0, or it's strictly greater than 0 but less than d, right? Those are the two possibilities. So this part is 1 minus xi. This is from here, right? This is from the definition. Plus, okay? So in order for this to be bigger than 0, my I has to be 1. And when this is bigger than 1, my yi has to be less than d, right? In order for it to happen, right? If my big I is 0, then nothing happened. So I have to make sure it will take value 1, means something happened. And I have to make sure the size of that should be less than the deductible. So 1 minus theta I plus, okay, so this is theta I. When or I should say this is xi. So when I condition on that, xi is y. So I want y to be less than d. That is exactly the CDF evaluated at d. So I proved the first one. The second one is somehow similar, right? So what I need to do is I need to, for any x greater than 0, for the continuous path, you have to analyze the CDF, not PDF. So we analyze so this means my xi is less than or equal to small x. So it may be 0 or strictly greater than 0, but less than small x. This part is a constant, right, which we already derived. So I just keep it. I don't want to write 1 minus xi plus 1 minus theta I plus theta I times the CDF. So let's analyze the second part. So again, in order for my x tilde to be strictly positive, plus, my big I has to be equal to 1, right? And then I condition on, well, you can put greater than or less than. Okay. So let's continue right down. This is a constant. I keep it. This is theta I. And this is, right, the, not here. It's actually x plus d. Okay. Or if you want, you can write one more step. Let's write one more step. Okay. Because given I equals 1, my x tilde equals y. So it will be y, and then I need to apply the deductible. Right? So plus theta I times Fy. Well, if you want, you can put I. Right? And then we differentiate on both sides with respect to small x, because that is the argument. Because this is a constant, right? So it's gone. So that's the reason why I don't write it out. Right? Remember here x is greater than 0. So we recover the second piece. That is y. But of course, it really doesn't hurt to think this as the probability at that point, right? Because here x is strictly greater than 0, so I must make sure my capitalized I is 1, so I have theta I down here. And when my capitalized I is 1, meaning something happened, and the size after modification is x, that means the size before modification is x plus d, because the modification is minus the deductible. Take the positive part. Right? Something already happened, so I know it's bigger than d. Here I want to be at x, so it will be x plus d. That's the that may help you understand, but that's not the rigorous part in mathematics. If you want to show it in mathematics, you should follow what I did. Or if you are advanced enough, you can use the idea of differentials, because usually what people write is the probability that, so assume this is continuous, okay? So now my x is continuous. So for a tiny increment, this is roughly the probability times the increment. So, well, you can use this because then dx will be canceled on both sides. You can work with PDF. So basically, the argument is that if you have a continuous random variable, talking about the probability at a single point doesn't make any sense. You need an interval. So this dx serves as the purpose to give you an interval. Right? So when you draw, well, it looks a little flat, but you can see this is continuous, right? So this is a graph of a PDF. The probability is the area. If you talk about a single point, there is no area. Area is in 2 dimensions, right? If you have a single line, there is no area. Area is 0. That is why the probability at any single point is 0 for a continuous random variable. You must have an interval. Then we can talk about area, right? So how do you get interval? You will go from one point to another point. So here I choose a tiny increment. It's very, very small, but it's an interval, right? 0, 0, 0, 0.1. Okay, it's small, but it's something. That is the analysis for the individual. Let's use the next page. We can be generous on that. So this is where is my cursor? Okay, let's move to the next page. Okay, then we do A2, individual, not individual, collective risk model. Actually, this part we did quite a lot in chapter 2. In this, we have like n is frequency, x is the claims size. So once you introduce our deductible, so we write, let's put tilde. Did I put tilde previously for S as well? So let's put S as well. So after the deductible, we use tilde to denote everything. Okay. So now the deductible has effect on N. Okay, N and So those two random variables, they are not the same anymore. The reason is simple, right? Big N counts the number of claims. After the introduction of a deductible, some of the claims are small. They are small enough that they do not contribute to the payment of an insurance company. So insurance companies simply throw them away. Right? Let's say deductible is 500. Then a policy with no claim and a policy with claim, let's say 100, they are treated the same because they eventually the company doesn't need to pay anything, right? So if nothing happened, of course the company doesn't need to pay anything. If something small happened with claim $100, the deductible is set at 500, the company doesn't pay either, right? So immediately we know until that will be small, right? So how do we count that? We introduce this, right? That is something we did before, right? So all we need to do is to count how big is it, right? If it's less than D, then it's not counted, okay? But if it's bigger than D, it will be counted. So what I mean is my new claim frequency will be equal to the sum from 1 to big N I. Okay, this is how I count the new claim frequency. This is how I count the new claim frequency, right? This is what we did in chapter 2, where we basically review everything. Of course, we know the probability. This is probability equals the survival of xi. This is probability equals the CDF, not x, not. Okay. That's the analysis on n tilde. Obviously, they are independent between n and capital I. So in general, we don't have very nice things of it. But if you know n is possum, then I know my new claim frequency are not equal. So it is also a Poisson distribution. And I further know my new parameter would be lambda times the survival. So assume all the x's have the same distribution. Okay, the reason it's straightforward, right? To prove this, that is because you can study the probability generating function if you want. If you want to study the probability generation of I or II, right? This is very obvious. So it will be 1 minus, or you can simply write the CDF if you want. So now I skip the index I times 1 because it's t to 0, so it's 1 plus the survival times t to the 1s, so it's t. If we further know PGF of n, we can calculate the PGF of n tilde, right? Then we can prove the previous result. But of course, if n is something different, right, you will not get a nice result as what we have for possum. So that is the effect on the claim frequency. And let's put a bullet point. So this would be right. So this is important. Let me circle here. Because we collect the new claims, right? That is the meaning of collective risk model, right? Previously, we collect all claims. Now we introduce deductible. We will only collect claims bigger than the deductible, right? Previously, you can think deductible is 0. There's no deductible. Now we have a positive deductible, so we will collect those bigger than deductible. So that's the most important thing is here, right? So with that in mind, so again, we derived this in chapter 2, but the understanding is straightforward, right? This is a conditional random variable. So you have a condition when you define it, right? So it's a payment event. So that's what we used to call a payment event, right? That is why you can also right now you can think a collective risk model is a model that collects all the payment events, right? So of course, the denominator takes care of the condition. And if this x tilde is equal to small x, then this big X will be small x plus d, right? That's the numerator part. So that is the analysis of deductible on both individual risk model and collective risk model. I think we also have the effect of policy limit. Policy limit is actually easier than the deductible because there are many things. It doesn't change. So let's do policy limit now. What did I put A? So now let's do B. Go to page 3. So let's do part B. So part B is effect of limit. Okay. Here since we only consider the effect of a single modification, so you can treat this as applied to the ground up loss. It will be more complicated if we have both deductible and limit at the same time. Then we need to be more specific on whether we apply this limit U to the loss or we apply this to the benefit. Okay, B1 is still individual risk model. So N is the same. They automatically capitalize. So the policy number, the number of policies, N is the same. Okay, that's clear because nothing changes the number of policy. Next, we want to study the impact on X. How would the X change? So let me give you the result first, and then we will analyze why this is the case. So again, we use tilde. So when we have tilde, that means it's, so first, let me give the result, the probability function, probability distribution function, probability density of my new xi is given by. So let's write down the result, and then we will analyze why that is the case. So here's theta I times fy at x for x bigger than 0, less than u. Here is theta I times we can use survival. Okay, 0 otherwise. Okay, so so basically your xi will be x. Right, so that means it's a minimum. So obviously, when your x is 0, your policy limit obviously is positive, right? So the minimum is still 0. So it doesn't affect anything if your value is 0. So that part is the same. Next, if your value is less than u, is still the same, right? So that's why if you compare with what we used to have, it's not here, but it's we know it's the same, right? For the first two piece. Now we want to know the third piece. Why is ended there, right? That the reason it's very simple, because if I have this equals u, that means my xi has to be greater than or equal to u, right? So anything more than u will be kept at u. So obviously this is bigger than 0. So I will need my big I to be 1 because I want something to happen, right? Right now I want the probability of the claim or of the loss to be bigger than the policy limit u. Of course, something needs to happen first. And then I need this. Okay, so this is obviously theta I. And once my big I is 1, my xi is the same as y. Right? I need my y to be bigger than u. So here I have, right? Otherwise it's 0, that's obvious, right? It will not be beyond u because it's capped at u. So it will not go more than u. It will not be less than 0. So it's otherwise it will be 0. That is the analysis on individual risk model. Next, let's take a look at collective. In this case, collective, it's somehow easy to study. Collective risk model. So first, n remains the same. The claim frequency. Okay, so random variable n remains the same. Okay, in our notation, n tilde equals n. The reason is as follows. If you introduce a policy limit, a claim is a claim. Right? You only change the size. You will not alter the fact that a loss will not be reported, right? Because here there's no deductible. Any loss will be reported no matter how small it is to the company, and the company needs to pay, even it is a small accident, right? Even it is as small as $10, the company is supposed to pay because there is no deductible. What changes is for big losses, right? So let's say the policy limit is $1,000 and there is an accident causing a payment of $2,000, then the company only pays $1,000, right? But it does not alter the fact of a payment event. But the company still pays, right? It's just that sometimes it will not pay the full amount. So that's why n remains the same, okay? The size obviously will change, right? The analysis for that is actually very simple. It's easier than the previous case. If your size is less than the policy limit, otherwise it's simply the survival function. Oh, not greater than. It's equal to the policy limit, and it will be 0 if x is some other values. Okay, again, it's straightforward, right? Because of the definition. Right? Anything beyond u is capped, so it has a probability mass at u. That's the probability when the original claim big X is bigger than the limit u. So that's the policy limit. Finally, we study stop loss. So that's actually a very simple idea. So simple that we already know everything. What is stop loss? So stop loss reinsurance. So you can think this as the deductible insurance on the aggregate. So this is a special type of insurance, okay, that insures against the aggregate loss as of an insurance company. So basically, in this business deal, the customer is the, so let me write down. So now in this deal, the customer or the policyholder is the insurance company. The insurance company with loss as. So usually we call the risk. So with risk S, okay, and the other party or the reinsurer is another insurance company. So or the underwriter. So it's a different. It's another insurance company. Okay. So basically, this is a business deal between two insurance companies. First, let's label them. Okay, insurance company A, another insurance company B. So basically, what A deals with are direct policyholders, like individuals, like anyone with a car needs to buy car insurance. Anyone with a house needs to buy home insurance. So basically, that's the business between individuals and the company A. So once company A have underwritten many policies, they collect premium, but they also bear the risk as the aggregate loss, right? Sometimes the size of the loss, somehow is manageable. The company may keep everything, but most likely, insurance companies, they don't like risk. They don't like collect all the premiums and sit on a huge potential, okay? Because the aggregate loss S can be realized in huge amount. They don't like that. So they would like to transfer some of the risk to another company for further assurance, okay? So they will negotiate with another company. Usually we call those reinsurers. So those are the companies you usually don't hear their names because they only deal business with other insurance companies, so called direct insure. So usually we call those direct insure. Okay. Usually the insurance companies you know of are direct insurers, such as Geico, such as State Farm. Those are direct insurers, most likely. What are the reinsurers? Like Munich Re, Swiss Re. Usually their name has a Re. Re means reinsurance, right? Uh, those are big reinsurers. So usually they do not take like auto insurance for like a business from you, right? They do business with direct insurers. Let's put plural, okay? So since S is the loss, right? So here the reinsurance contracts, it's somehow a safe contract between direct insurer and the reinsurer on the aggregate. So if you apply deductible on the aggregate, that's what we call the stop loss. So so basically, stop loss is just this. This is stop loss, right? So the risk of this contract is the aggregate loss S, and you're going to apply a deductible D on the entire aggregate. Previously in chapter 2, when we study deductible, it's deductible on individual policy, right, or on individual claim. That is what we did also here. When we apply deductible, it is a deductible on X, on each policy or on each claim. But now we want to apply this deductible on the entire aggregate. That is the difference between a standard deductible insurance and the stop loss. Stop loss, this is applied on an aggregate level. So mathematically speaking, the difference is whether you apply deductible and then do summation, or you do summation first and then apply deductible, right? So that's the difference, mathematical difference. This, we have seen this type of question many, many times. So I don't think it's necessary to analyze this, right? We have the standard formula. For instance, we know this is the survival function of S, dx. This is a useful formula we usually apply, or you can apply definition directly if you prefer. So I will stop here for the general part. I think we should, I will do a few more exercises or examples in the next video.